Good morning, students. Today I am taking your second presentation class. Uh, this would be on Unit 3 and the numericals I will discuss. These numericals would be actually on the topics which I discussed in last presentation. I discussed in last presentation about equation of kinematics and work energy principles, work energy equation. So I would be discussing in next slides numericals based on those two things, and remaining other principles numericals I will discuss in next presentation, right? So this presentation would be on those numeric would be on those this this presentation would be on uh, on those things about equation of kinematics and work energy principle, right? Now let's go ahead. Now, this first three numericals I will be discussing on equation of kinematics. Like in this case, there is a numerical that an airplane accelerates down a runway at 3.2 meter per second square for 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. Now, this is a very easy numerical. You already are aware of these type of vehicle. I'm just trying to recall these things again to you. Now in this case it is being given that we have to find a distance of aeroplane before it takes off, right? So here we know that the initial velocity of airplane is 0, vi is equal to 0, and time which is equal to 32.8 second, and acceleration is acceleration is also given 3.2 meter per second square, right? So if now to find out the of distance, we know the formula is s equal to ut plus 1 by 2 at square. Here the formula is given in another way, that is d equal to vi into t plus 0.5 into a into t square. This t2 is actually basically t square. Take it as a t square, right? Okay. Now uh, as we know that vi is equal to 0, t is equal to 32.8 second, a is 3.2 meter per second square, and t2 t is 32.8 second. So when we put all this formula, we after calculation we get d equal to 1720 meter. Do take care of the unit, and always write the unit also after solving, because unit has a very big role in numericals. If you write wrong unit, or if you do not write unit, then the answer then the answer would totally get changed, right? So this is the first question which I wanted to discuss. The next numerical here is a race car accelerates uniformly from 18.5 meter per second to 46.1 meter per second in 2.4 second in 2.47 seconds. Determine the acceleration of the car and the distance traveled. So here we are talking about a race car where we understand that the acceleration of the car is uniform, and it starts from u equal to 18.5 meter per second, that is initial velocity 18.5 meter second, and the final velocity 46.1 meter per second, and this happens in time 2.47 second. We have to find here acceleration of the car as well as the distance traveled. So first to find out acceleration, we know a equal to dv upon dt or delta v upon t, where delta v is actually basically difference of final velocity and initial velocity. So and t is given 2.47 second. So if we put a equal to 46.1 meter per second minus 18.5 meter per second divided by 2.47 second, where 46.1 meters per second is final velocity, 18.5 meter per second is initial velocity, and t equal to 2.47 second, then we can find out acceleration, which would be 11.2 meter per second square after solving, right? So this is how we have found acceleration. The next thing is to find out a distance. Now we have to use the same formula which we used in last numerical, that d equal to vi into t plus 0.5 into a into t square, right? So again putting the value of vi, t, a and t. So we after putting d equal to 18.5 meter per second into 2.47 second plus 0.5 into 11.2 meter per second square into 2.47 second square, we get d equal to 79.8 meter. So finally we calculated acceleration equal to 11.2 meter per second square and distance equal to 79.8 meter. These two are the answers of the numerical which we had just done, right? So now let's go to the next numerical. The next numerical is a plane has a takeoff speed of 88.3 meter per second and requires 1365 meter to reach that speed. Determine the acceleration of the plane and the time required to reach this speed. Uh, Here we are talking about a plane which is taking off, and the takeoff speed was 88.3 meter per second, and to reach uh, to the height 1365 meter, uh, uh, um, this speed is actually required, right? So here we have to find the acceleration of the plane and the time required to reach that speed. So, to find out acceleration, uh, the formula which because here we know initial velocity, final velocity, and distance also. So, the formula which we are going to use is v square minus u square equal to 2as. Here, in this numerical answer, the formula is given in another way, that vf2 equal to vi2 plus 2a into d, where vf2 is final velocity, vf square is final velocity, vi square, these are square, not 2, sorry, I also spoke wrongly. Vf square, which is final velocity square of final velocity, vi square is initial velocity square, a is acceleration, and d is distance. When we put all this formula, all the values of this formula, so we get 88.3 meter per second per square, which is equal to 0 meter per second square, where 0 is initial velocity, plus 2a into 1365 meter. After solving, we get acceleration equal to 2.86 meter per second square, right? Now let's go ahead. Now again we have to find time. So the next formula which we are going to use is v equal to u plus at, because we know final velocity, initial velocity, acceleration, but we do not know time. So after putting uh, in the formula vf equal to vi plus a into t, we get 88.3 meter per second equal to 0 meter per second plus 2.86 meter per second square into t, and after solving we get t equal to 30.8 meter 38.8 second. So we get the answer, a acceleration equal to 2.86 meter per second square and time equal to 30.8 second. So these two are the answers of this numerical we just now discussed. Now let's go to the next part. Now next two or three numericals which I will discuss is based upon work energy principle. Equation of kinematics we have understood. I will try to do either give assignment or more numericals and in another presentation, right? If we get time, right? I also request you student to do numericals of AK Tayar also, as you are having at your home. So keep practicing those numericals also, right? So now, okay, let's go ahead to the numericals based on work energy principle. Now here in this numerical, uh, okay, now before starting question, we know, as I have told you in last presentation, that work energy principle is basically work done is equal to kinetic energy, uh, uh, final kinetic energy minus initial kinetic energy, right? So this formula which we are going to use in solving this numerical. Now the numerical here is a 10 kg crate slides down a 4 meter long ramp at 30 degree to the horizontal, on which it has a friction coefficient of about zero point 0.2. It was pushed off at an initial speed of 1 meter per second. Estimate the speed at which it arrives at the bottom. So here we know that there is a crate which has a mass 10 kg that will slide down on a ramp which is actually 30 degree with horizontal, and the length of the ramp is 4 meter long, right? And coefficient of friction is zero point 0.2, and the initial speed which with which this ramp with which this crate was pushed, that speed is 1 meter per second. So we have to find out the final speed when it arrives at the bottom, right? So we are using work energy principle. Now, as I told you that the work energy principle basically means work done equal to final kinetic energy minus initial kinetic energy. So first of all, we will find initial kinetic energy, which will be equal to 1 by 2 mv 1 square, where m is known, that is 10 kg, and v1 is also known, that is 1 meter per second. So um, after solving both of them, after solving this, we get initial kinetic energy 5 joules. Now, another our final kinetic energy is 1 by 2 mv 2 square, where v2 is the final velocity and which we have to find. So definitely m is known, but v2 is not known, which we have to find. So we are keeping this intact here, right? Now, and now we have to find the work done. So the left hand side of the work energy principle is work done, and here if we see that work done is basically done in two ways. One due to weight, and another due to friction. So we have to find out work done in both the ways, weight and friction, and add them up. That will be the total work done. Now, due to weight, we know that work done would be mgh, where m is known, g is known, but h is not known, right? So to know, but we know the length of the ram, and as well as the angle it makes with the horizontal is 30 degree. So if we use if we find out the height, uh, if we find out this height, then um, then we get the formula is 4 cos 60 degree, and we get the height 2 meter, and when we put this, we get work done, which is equal to 196.2 joules, right? Now, to find out weight, sorry, work done due to friction, we know that the friction is frictional force into distance, and this is opposite to the motion, so it will be negative, right? So now frictional force is basically mu into n, where mu we know, but n here, n is in downward direction, and there will be opposite force mg cos 30 degree in at this side. So n will be equal to mg cos 30 degree. This you already know it. In case you do not understand this thing, that n is basically downward and mg cos 30 degrees upward, so n will be equal to mg cos 30 degree. If you don't understand, we can talk this thing on Zoom meeting also, right? So this mu mg cos 30 degree, once we solve this, mu we know 0.2, m we know 10 kg, g we know 10 meter per second square. Putting the value of cos 30 degree, we get answer 17 newton, and uh, putting this f in this value here, and as the distance is 4 meter. This we already know, that the movement of crate from this to this, and the distance is 4 meter, so we know s also, so this is 4 meter. So when we solve this, we get minus 68 joules. So now we know work done due to weight also, done due to friction also, which is negative in nature. So when we put both these values, we get total work, that is w equal to w plus wf, and we get the answer 128.2 joules, right? So now we know work also, we know initial kinetic energy also. So we put both the values, and we get answer 1 by 2 mv2 square equal to 5 plus 128.2, and finally we get final kinetic energy as 133.2 joules. And putting the value of m, we can solve for v2 also, and we get the v2 equal to 5.16 meter per second. So this is how we uh, we apply the work energy principle, and this is one of the numerical which I wanted to share with you. More numericals you can find in AK Tayal also, so start doing them also. Um, first do uh, first do those numericals which were solved, and then you can go into the numericals which were unsolved, right? So okay, fine. Next, let's go ahead to another numerical. Just a minute. Just a minute. Just a minute. Now this is another numerical. In this numerical, it is given in a piece of machinery. A 20-gram collar is lifted. This is a this is a collar which is lifted from one end of the rod. Here it is lifted from this to the other by a spring. This is a spring, right? Figure 33a. This is the figure 33a, shows the initial position when the collar is released, neglecting friction. Estimate the speed with which the collar arrived at the other end. We have to estimate the velocity when it reaches, this collar reaches uh, from here to here, right? And the spring has a free length of 20 millimeter and stiffness 100 Newton per meter. We know the free length, that is 20 millimeter, right? So now again we are going to use work energy principle. We have to find the final velocity, right? So initial velocity we know 0, so definitely initial kinetic energy would be 0, that is 1 by 2 mv1 square, so that will be 0. Just a minute, this will be 0. And then uh, kinetic energy, final kinetic energy is equal to 1 by m 1 by 2 m v2 square, which we have to find because we have to find v2 actually. So this we are keeping intact here. And next we find the work done. uh, Now work done is basically here in by two ways: one due to weight, another due to spring loss of strain energy, right? So we will find both the work done and add them up, and that will be the total work done. So first due to weight, it is minus mgh, because collar moves upward, right? From here to here, it will be against the motion, or due to gravity against this. So this will be minus mgh, right? uh, Now we put the formula of m, g and h. Here is 80 mm. This is from here to here we have to move. So this 80 mm would be the h. So when we uh, put all this the values, we get work done due to weight 0.016 joules, right? Now next thing is work done by spring, which is equal to spring loss of strain energy, right? So this will be equal to S1 minus S2, that is the spring energy when the collar is here, and the spring energy when it reaches here. So S1 is the spring energy at this point, and S2 is the spring energy when it reaches this point, right? Okay. So then we know that the spring energy formula is 1 by 2 kx square. Here x is actually e, small e we are taking. So that initial kinetic energy is 1 by 2 ke1 square minus 1 by 2 ke2 square. Now here, first of all, we have to find the e1, right? We know the total length of uh, spring is 120 mm, and the free length of spring is 20 mm. So E1 will be equal to 1 by 20 minus 20 mm, right? So we get zero point 0.1 meter. After changing millimeter into meter, we get answer 0.1 meter. Similarly, E2 here, uh, the 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 actual collar would be collar when the collar would reach here, then the length of the spring would be 120 minus 80 40 mm, and the free length is 20 mm. So E2 will be equal to 40 mm minus 20 mm, and finally we get 0.02 meter after changing millimeter into meter, right? So this is the one thing. Now we we find the ws, that is spring force, putting all the values. Value of k, the spring constant, we know that is 100 newton per meter. So putting the value of e1, e2 and k, we get spring force, spring work done equal to 0.48 joules after solving all those things. So now we know spring work done as well as we know work done due to weight. Putting both the values, we get total work done, that is ws plus ww, where ws, that is spring weight, is 0.48 joules, and ww is just a second, ww is 0.016 minus 0.016. So when we put both the values, we get total work done 0.46 joules. So now we have found total work done, we have found initial kinetic energy, we have to find final kinetic energy. So when we put in this formula, we basically get final kinetic energy as 0.46 joules, and when we put the value of m, we get finally V2, which is equal to 6.8 meter per second. So this is how we can apply work energy principle. Another way, I have showed the another way of implementing work energy principle in another numerical. So now we have another numerical on work energy principle. This, according to this example, the gearing of a small motor car of mass 880 kg is such that the engine turns 25 radians for each meter of the car's advance. We know the mass of the car is 880 kg, and engine turning is 25 radian for each meter. Every meter car moves, there will be a engine rotation of 25 radian, right? So if you go ahead, the engine produces an average output torque of 40 newton meter. We know the output torque, that is 40 newton meter, and for an initial speed of 1 meter per second, the initial speed is 1 meter per second. Estimate the speed, that is final speed, when a distance of 12 meter has been covered. When distance of 12 meter has been covered, uh, that velocity we have to find. Initial speed is given. Neglect air resistance for this low speed, and neglect the second movement of mass of the wheels. Now this question can also be solved using work energy procedure. Uh, Now, as we know, the initial velocity here, that is 1 meter per second, and final velocity we have to determine. So the initial kinetic energy will be 1 by 2 mv1 square, where m is 80 kg and v1 is 1 meter per second. So after solving, we get 440 joules, and the final kinetic energy is 1 by 2 mv2 square, where v2 is we have to find. So we are keeping k2 intact here, and let's go ahead. Now the next thing is we have to find out the work done. Now here the work done will be done in two ways. One, because of this rolling resistance, that friction here at this place, right? The movement of car causes frictional work done. Also, they have to oppose the frictional force. So because of this, work has to be done. Another work done is because of this movement of engine, this output torque of engine, that work done we also find, that engine work we also have to find, which is equal to m into theta. That is, m is torque and theta is the total movement of the engine. Now, first of all, we will find the frictional work done, that is rolling frictional force into distance, where this will be mu r into n n will be equal to mg. The This mg and mu n mu mg is this side, n is above side, so mu n will be equal to mu mg. And in numerical, the mu is not given. I'm just telling you the mu you have to take is 0.01. So take this value 0.01 mu, right? And put the value of m and g. Finally you find that frictional work done is 1036 joules, right? So now let's go ahead. uh, Now the work done due to engine will be m into theta, where m is the torque, which we all know, but theta here we have given for 1 meter there is 25 radian theta. So if there would be 12-meter movement, then the theta would be 12 into 25, it will be equal to 300 radian. So when we put this 300 radian in this formula, we get 12,000 joules. So total work done will be equal to this work done plus this work done, and finally we put this value, we get answer 10,964 joules. So we know total work done, we know initial kinetic energy, and we put in this formula, we get final kinetic energy, that is equal to 11,404 joules. So if we know the mass we know the mass here 880 kg. If we put this mass here, we get final velocity that is 5.1 meter per second. So I hope uh, uh, these three numericals have made you understood about how to implement work energy principle, work energy equation. So these three numericals I have discussed on equation of kinematics. So this is to make you understand how these two principles are used in numericals. You can do more numericals on A from AK Tayar also. Plus, I will try to give you some assignment also, right? Uh, this is for today. I hope you have liked this presentation. If you have liked this presentation, give your comments in on YouTube video also. That will be taken as your attendance. Thank you. Thanks a lot.